Welcome back, everyone. We are moving on to sequences. So this will be a several video, sequence. So this video, we're just going to do some very basic definitions, tell you what a sequence is, what a subsequence, what a tail is, and then what we mean when we use the word eventually. And we'll finish with a couple of examples. All right, so let's get started. So first, what is a sequence? So we're going to start with, kind of a very, very short definition of it, and then we'll expand on it. But the expansion will be short too. So a good way to think of what is a sequence. So a sequence is an ordered list. So we've even talked a little bit about this already. So the idea here, right, you have a whole bunch of, terms, real numbers, say, for example, and you put them in an ordered list, meaning you are going to list them out, and the order does matter. So you might say 1, and then pi, and then 3.8, and then the square root of 2. Okay, and I cannot change the first two, right? It was 1 and then pi. I cannot go pi and then 1. Okay, and I can just list them all out, and you can ask me what is the 18th item in the list, and I would tell you that it is e to the pith power. Okay, so maybe a more mathematically precise definition, you could say a sequence is a function whose domain is the positive integers. Okay, so that's the whole thing where you can ask me what the 18th one is, right? What's the first item in the list? What's the second item in the list? What's the third item in the list? What you can't ask me is what is the pith element of the list, right? So I'm only allowed to ask about, right, 1, 2, 3, 4, 5, right? Those elements in the list. Okay, the notation that we're going to use is, I'd say known but mostly non-standard. I'm going to use a dot. So the sequence would be called A, but I'm going to put a dot down here, and you're going to see why in a second. Alternate notation that you might see is you'll write down something like A sub k, and then maybe you'll put a little k greater than or equal to 1 just to let you know this k starts at 1. But of course, because the domain is the positive integers, when we say this, we're not allowed to use like k equals 1.5. Okay, and if we wrote this out more fully, we would say you have A1, A2, A3, etc. And we use these parentheses here to indicate, hey, this is an ordered list. It's not just a set. Okay. Now, we'd said it is a function. Yeah, so function notation, how would that work here? Well, if a is the name of the function, then typically, you'd write something like a of k. And so what is a of k? Well, a of k is just what happens when you take, of course, the same a dot, that's the longer name for it, of k. But really, what is it in this list? Well, this is a sub k. Okay, so you'll see us use, I'm typically not going to use the dot notation if I was going to write a of k, but in practice, I'm just going to write a sub k most of the time anyway. But if I just want to name the sequence, I'm going to use this dot. And that dot is there to remind you that something goes there, right? There's some sort of index that we need, a 1, a 2, a 3, in every position. But I don't want to necessarily have to write down a letter to do this. Okay, I can just write down A for the name of the sequence, and then that dot just tells you, hey, we have to put something in that spot. Okay, as I said, we're going to distinguish between sequences and sets. And so one way I might do that is say, well, if this was a set, then the A1, the A2, and the A3 would be elements. So instead of calling these the elements of the sequence, we're going to call them the terms of the sequence. Okay, that's just there to help us not get confused. All right, so that's what a sequence is. Now, very quickly, when you're working with sequences, you realize you also need to look at what are called subsequences. So a subsequence is where you're going to get rid of certain terms in the sequence and just look at whatever's left over. Okay, that seems pretty reasonable. How do we make it mathematically precise? So here we go. If A dot is a sequence, then what I want to do, right, I want to get rid of things from A dot. So I'm only going to be looking at maybe, I don't know, the third term and the eighth term and the 11th term and the 100th term, something like that. So when I'm doing that is I'm actually looking at some other sequence, right? It's an increasing sequence of the terms that I'm actually going to be using. So, okay, let's write that down. A is a sequence, and let's call it n dot. Okay, this is going to be an increasing. In fact, I want it to be strictly increasing because I don't want to use the same term twice. So a strictly increasing sequence of positive integers because I only want to choose, like I said, the third or the eighth and the 11th and the 100th, right? So I just want positive integers because that's what the domain is here. Okay, so I have a sequence and then I take a strictly increasing sequence of positive integers. We call that n dot. So when I say this strictly increasing sequence, right, what do I mean? I mean that I have n1 less than n2 less than n3 and so forth. Okay. So what I can do now is I can, well, because everything here, these are functions, right? Sequences are functions, I can compose them. So I look at the composition where I'm going to compose A dot with N dot. And when I do that, now A dot is only going to see the image of N dot. And the image of N dot are all these numbers here, right? N1, N2, N3, etc. Okay, so that's how I can mathematically, right, write down what it is to be a subsequence. Now, notationally, we're not going to want to write A dot composed N dot all the time. And so, much like we did up above, we're going to compress the notation. And we're going to take the A and we're the N, and then we'll put a dot down below. And so then what do these terms look like? You'll have AN1 and AN2 and AN3 and so forth. Okay, and so this is called a subsequence. Right, of A dot, right, or just of A. Okay, fine. Now there's a very particular type of subsequence that we're going to want to talk about quite a bit. So let's say I choose some index, call it M. Right? Then I look at the subsequence, which corresponds not to just some random, right, strictly increasing sequence, but to the one that starts at M and uses M and M plus 1 and M plus 2 and M plus 3 and so forth. So it's basically picking up somewhere in my original sequence A, all right? So I start somewhere. Maybe I start at A4, and then I get all the terms, right, after that. So I look at the subsequence, which I'm going to call A greater than or equal to M. Okay, so this is itself a sequence, and it's the subsequence that starts at A sub M and then just continues on. So it's like you just chopped off part of the sequence A, and now you get what's left over. And what's left over is called the tail of the sequence. So this is called a tail of A dot. And of course, there's an infinite number of tails because I could do this chop, right? I could start at anywhere in the sequence. Right? In fact, I could do, well, I mean, one tail is I could just start at A1, right? It's kind of a silly tail. Okay, but I could do it. Or I could start at 100 and I'd have A100 and A101 and so forth. Okay, so we're going to be interested in these tails because with sequences, it turns out what happens in the beginning is just not all that important. It's what happens in tails that actually are relevant. Now, having said that, we're very often going to be talking about properties of sequences, and the property may hold for all the terms in the sequence, or it may only hold in a tail of the sequence, or it may not hold at all, or it may just hold randomly. But in that special case, where a property holds for all the terms in a tail, then we get a special word. So if a property holds for all terms in the tail of a sequence A, then we say that that property holds eventually for A, or eventually that property holds for A. So then the property eventually, okay, that's the whole point of the tail, right? You don't start in the tail, maybe you have to go out to the 150th place, and then all of a sudden this property starts holding. So that's what we mean when we as mathematicians say eventually this holds for a sequence. So then the property eventually holds for A dot. All right, so that's our definition. So let's get to a few examples. So how about we let A dot be the sequence 2, 4, 6, 8, 10, etc. So these are the even integers. Okay, so that's an example of a sequence. Now let me look at B dot. B dot is going to be 4, 8, 12, 16, etc. This is actually a subsequence of A dot. Now, it's a subsequence of A dot because, well, how did we get it? Well, I just started eliminating terms, right? I just took the 4, the 8, of course the next bit here would be the 12, etc. Okay, and I got rid of the 2, the 6, and the 10, all of the terms that were congruent to 2 mod 4. Okay, so I just have the multiples of 4 in B. Okay, so B is a subsequence. However, B is not a tail. So it is not a tail of A. And it's not a tail because there's no point at which, okay, now I'm just getting all the rest of the terms of A. I keep skipping every other term in A. Okay, so B is a subsequence, but it's not a tail. Okay, of course, this is a, just one example, right? Like there's lots and lots of examples we could write down. But if I did write down, how about C dot, and I could have 6, 8, 10, 12, etc. This is a subsequence of A, because all I'm doing is I'm getting rid of the first two terms, and then I get all the rest. In fact, because I get all the rest, right, I'm starting at the third term, this is a tail. Okay, and in fact, I might write C dot is equal to A greater than or equal to 3, because I'm starting in the third term, right? The 6 is the third term of the sequence A. Okay. What about the sequence, let's call it D now. So D is going to be 2, 3, 4, 6, 8, 10, and, well, something. I don't even know what's coming, but one thing I can immediately say is that this, while being a sequence, is not a subsequence of A, because it's got this 3 here in the second position, and 3 does not show up in A. So this, it is a sequence, but it's not a subsequence of A. Okay. How about a good non-example? So if I look at the set of real numbers, the set of real numbers is not a sequence. Okay, how do I know it's not a sequence? Well, there's two really good reasons here I can immediately write down. Number one, a sequence, let's go back up, is a function whose domain is the positive integers. The set of real numbers is a set. R is a set, not a function with domain the positive integers. Okay, so now maybe you might say, well, okay, that's not what I meant. I didn't mean that you just write down randomly all the elements of the real numbers. I mean, I want to write them down in order. Okay, and there's where we get back to our lesson on cardinality. We know that the real numbers are uncountable. All right, R is uncountable. And what that meant is that there was no bijection from the real numbers to the positive integers, or, if you like the other way around, from the positive integers to the real numbers. Okay, so there does not exist a bijection from the positive integers to the real numbers, which means you can't view the real numbers, okay, as some ordered list from the positive, right, with the positive integers as our domain. Okay, so real numbers, good example of something which is not going to be a sequence. In fact, anything uncountable, you're not going to be able to write down as a sequence. Now, just for those of you who are interested in going a little bit further with all this, there is a way of generalizing the notion of a sequence a bit so that you can have your inputs, your domain, not just be the positive integers, but actually be things like the real numbers. So that's a subject we're not going to get into in this class, but if you want to look that up, they're called nets, and that's quite interesting. All right, we'll see you all next time.